Good, and everything else looks good. All right. All right, so I got a few things that are kind of new and two new modules that I recently wrote because I thought that might be helpful to some of us in this class. The first one is TTP ASM code execution tracing. So let me just kind of show you what it looks like. It's nothing new, okay? It is nothing new. It's just that I put everything kind of together. Um, it shows you, how to trace the code execution manually, and it shows you, okay, you can run the command on the command line, like this, and then what steps you need to do to import the trace file into the spreadsheet, and then the other one is to use River Spider. So this one includes a link to the zip file, and if you're using Windows, it also includes Windows specific instructions to set it up. So it will take you some time to set it up and read the instructions carefully.
Took me quite a while. I still didn't finish, but
Yeah.
took a while. If you don't know what no Linux, the Ubuntu the interface was good.
Yeah, so you're using Mac OS, which is close to Linux.
Mm-hmm.
So there's only a little bit of instruction that is a little different.
Mm-hmm.
So
My home computer is a PC though.
oh, your home computer.
So I was like,
Oh, so you're setting it up on your home PC?
Yeah.
I see. Okay, so if you're using a PC, then you have to use the Windows specific instructions. And Omer was a student in one of the previous classes, so he wrote both the Mac OS and also the Windows instructions. I only provided the Linux instructions originally. Um, so did you finish the whole setup?
Almost.
Almost.
I got most. I just had to change some of the path names because it wasn't finding the stuff.
Oh, okay. Yep. Okay. That's actually a useful experience, because that's how you kind of set up tools to get it working. A lot of times, you get tools to install, but many times you still need to tweak something for them to work, the way that you want them to work. So there's that. But I also kind of wrote a little bit about, how to use the trace, why it's going to be useful in terms of, debugging your programs. So I wrote a little bit here, and I did not get too far, but I got far enough to kind of wrote down, all of these particular parts. So I can read this if you want to, if you want to kind of figure out how to use River Spider, or really just the trace ability to analyze your code and help you debug your code. So that's one. The other one is I'm going to get into structures today, and pointers and stuff like that. Do Are you guys all good with the homework assignment, or do you want me to go over it?
Can we go over it?
Yeah, I can go over that. Okay, so let's go over the homework assignment, which is implementing the swap subroutine. That is in, I'm just looking at the function calls. That's it. So function calls is the one. So this is the assignment that was due just a few minutes ago. Not sure how many people finished, but that's okay. All right, so the key to this homework assignment is there is the source code in one of the questions. I think it's, nope, not this one. Maybe question number 4. There we go. Okay, so question number 4 contains both the C code and also part of the assembly code. So the assembly code here is really just main, and then swap is not implemented because that's kind of what I wanted you guys to do. So I'm going to start with this one. Okay, so let me copy and paste the C code first, and then I'll display the C code and also the assembly code side by side. So this way we can kind of take a look at both at the same time. So this is going to be swap.c, which is the C code. Copy and paste, done. And then we'll go ahead and do the same thing with swap.ttpasm. And that's going to be the assembly code, which is here. All right, copy and paste. And then Control D. Let me turn off the notification. The notification specifically is just reminding me that I have a class to teach. There are There, I think Google actually made some of the reminders to be location specific, so you can actually use the location to turn on and turn off the notification. I'm not sure about the resolution, whether it has enough resolution to tell whether I'm in a classroom versus my office, because they're actually pretty close and both are indoor. So the GPS resolution may not be very good in that case. All right, so we'll take a look at the C code and then take a look at the um, assembly code, like so, side by side. And I can make this wider, so this way we can actually display more stuff. And that actually looks good because the C code doesn't have a whole lot of comments, so I don't want it to be too wide. All right, so we'll go ahead and start with the assembly code. So you don't need to change main at all. Okay, so main is already provided. Just kind of leave it as is. The only thing you might want to change is just to add a no-op instruction if you want to use River Spider to trace this code. So that's the only thing. So when we get to the swap subroutine, the way I make things work is I always put in the return code first because that's one thing that I keep forgetting to do. So since I know my own favorite mistakes, so I would kind of do it in a more structured way. And then the other thing I want to do is to look at what is on the stack at the time. So the stack has two parameters, PTR2, PTR1 are the two parameters, and then the return address, and then also the local variable t. So those are the 4 bytes on the stack that I can count on. So now we can have PTR2, which has the highest memory address, and then we have PTR1, which is 1 byte below PTR2, and then we have the return address. So when the caller is done, this is what register D should be pointing at, because this is the last thing that the caller, which is main in this case, is pushing on the stack. But I also have a local variable T, and the register D should point here after local variable allocation. So this is at entry point of the function. So I just want to make it very clear because register D points to only the return address at the entry point of swap, but I do want to allocate one additional byte for my local variable T. So is that picture okay so far? So when you guys are writing your code, I would also recommend using some way to kind of so that you can visualize what is expected on the stack, where the stack pointer is pointing to. All right, so given these, there are a few ways to do the swap subroutine. If you do not want to follow the C code, that's kind of like a quicker way to do it, okay? But if you want to follow the C code, it's a little bit more tedious, but it's a good exercise. So in this case, I want to follow the C code. So I'm going to say p swap t is at offset 0 after allocation. And then we have swap lvs being swap underscore t1 plus. This one here is the size of t as a local variable. So when I add the displacement of where I can find t and the size of t, I get to the total number of bytes that I need for local variables. And then we have swap underscore ptr1, which is swap lvs1 plus. This one is referring to the size of the return address because there's the return address between ptr1 and local variable t. And then the last one is ptr2, which is swap ptr1 1 plus. This one here is referring to the size of ptr1, which is really just a pointer. But every pointer in TTP is just 1 byte wide because the architecture itself is an 8-bit architecture. So we do okay so far with the label definitions. Okay, all right. So with the label definitions, I can then also start with just allocating and deallocating for the local variables. So LDI probably a safer idea to use B, swap underscore LVS, and then we do a subtract register B from register D. So whenever you subtract, you're allocating more things on the stack. More things are being in use. So this is for allocation. And then this is for deallocation, changing the sub to an add. so we are deallocating at that point. So now on line 44, I can actually start to write the code corresponding to swap in the subroutine. So are we okay so far with all the steps that I have taken? All right. So now we look at the first line, which is line 4 in the C code. We need to get to the right-hand side. So to get to the right-hand side, this is going to look super boring after a while because there's a certain pattern to the whole thing. So swap PTR1. This will get the offset of where to find PTR1 relative to where the stack point is pointing to into register A. It is not an address. This will make register A the address of PTR1, but that's not what I'm interested in. I'm interested in what PTR1 is pointing to. Now I just have the address of PTR1, so I need to do a LDAA to get to PTR1, and then I need another LDAA to get to what PTR1 is pointing to. So that's why this is the right hand side of line 4. The left-hand side is very much similar. So we have swap underscore t, add bd. This is now, register b is now the address of local variable t. And that's what I need, okay, in this case. So I can now store whatever register a has, which is the value of the right-hand side of the assignment, to wherever register b is pointing to, because register b is the address of the left-hand side. So that will get line 4 done. Are there any questions about this part? So once again, it is important that I would also upload this code so you guys can have it, and you can comment it line by line and try to figure out how each register that is affected by each line, and kind of understand how it relates to the C code and also how items are arranged on the stack. All right, so line 2 is kind of the same deal, okay? Very much the same. So since I'm a little bit on the lazy side, I'm just gonna copy, paste, and modify. Except this time we have PTR2, and then the other side is a little bit different, okay, but not by much. So we have LDI B swap underscore PTR1, and then we have add BD LDBB. So this time we do need a one LDBB before we do the store, because register B, on line 60 contains PTR1. I don't want to change PTR1, the parameter. I want to change what the parameter is pointing to. That's why I need a store after the LD in this case, and that's line 5 in the code. And line 6 is kind of a mix between line 4 and line 6, because we're just changing which side has the reference to the local variable t. So in this case, let me see. Okay, I'm just thinking about whether to copy and paste or not. Yeah, maybe not. So this time I have swap underscore t in register A. And this time only one LDAA, because t has the value that I want already. T is not a pointer. I'm not dereferencing t. So now on the other side, we have something very similar to the previous line, except this time we are dealing with PTR2. So we have swap underscore PTR2, add, BD, LD, BB, and STBA. And that should be the entire thing. All right. Are we okay so far with this code? All right. So assuming that we are okay with this code, we can now try to run it. And I want to make sure that I save the program, because that's one thing that I always kind of forget to do, is not saving it first before I try to run it. So now I go to River Spider and submit the code, which is swap.ttpasm. All right, so the object code is good. It's getting into the simulator. It is done. So now we can go back to look at the code here. Takes a little bit of time to refresh, just because it depends on the server load on in the Google data center in this case. All right, so what I'm really looking for is the initial content at location FE and also at location FF. So we have FE, location FE has had the content of 03, and location FF had the content of 07. So what I'm looking for is having these two values to be exchanged. In other words, if the program worked correctly, I would end up with 03 in location FF and 07 in location FE. So that's pretty easy to search for because you can do a control H and really just kind of search for FF getting the content of 03. If it's missing entirely, then I know the program did not work. So let's go find. There we go. Okay, so we found that one. And we also found FE getting 07. So I know the swap part is done correctly. But if I mess up the return or somehow I mess up the stack forgetting to deallocate local variables, it would not return correctly and the program would not conclude correctly. So I look at the end here. The stack pointer is returning back to the value of 00. That's good. And that's right before the halt instruction. So I think everything is actually working correctly in this case. So is that okay? Is that helping? All right. Any questions related to the swap subroutine? No questions? All right. So if there are no questions about this, then we're going to get into the last topic of this entire class, which is pointers and structures. Um, I'm not going to talk about arrays too much, except for arrays of characters, because an array of structures, it's not very easy to do using a Textoid processor, because I don't have a hardware multiplication instruction, so that makes it kind of hard to use. So instead of doing that, we'll go ahead and take a look at some structure program using structures and translate that into TTP ASM. Forgot the -O, so it's not displaying things side by side. There we go. All right. So I'm going to pound include stdint.h, standard integer.h. And I'm going to define a really simple structure here. This is structure x. And inside here, I will have two members, okay? One member is uint 8 underscore t. This is the value, okay? So we have b here. And then we have struct x pointed to by next, okay? And typically, my usual convention is the variable name kind of helps to identify what it is. So this is a pointer to the next structure. All right, so I should probably pause here and explain that struct is really kind of the more primitive version of class. So if you know what a class is or what a class keyword does in object-oriented programming, struct is kind of the same thing, except it's a lot more primitive, okay? Because inside the class, you can have methods, right? You have control over the scope. You got private, protected, and public members, right? Well, with a struct, especially when we are only writing in C, not C++, a struct is basically a class that cannot have methods, and everything is public. That's it. Okay? In other words, it is a very simplified version of a class. It's a very primitive concept related to classes. Are we doing okay so far? So these lines from line 3 to line 7 doesn't actually generate anything. It really is just a description of what a struct X is. Okay, but at this point, I don't have a variable of this type. I'm making the cookie cutter, but I haven't made any cookies yet. Okay, all right. All right, so we are going to take a look at one. Okay, so we can look at a subroutine, and we can make the subroutine do return a void. Okay, we'll say link Um, and then it has two structures. Okay, the first one is struct X, and with this one, both of these can be pointers. Okay, so ptr1 and then struct X ptr2. Oops. And what I want to do in link is simply to make ptr1, the structure pointed to by ptr1, and change its p next to point to ptr2. That's all I wanted to do. So we have ptr1 points to p next, and that would be changed to ptr2. That's all I wanted to do. Okay, so before we proceed any further, are there any questions about the way the structure is defined or about line 11, which is the only thing that I want the subroutine to do? There are no questions about line 6, where we have a pointer to the very same structure that I'm actually trying to define. Okay?
Is there something weird about that?
Only if you try to overthink. Which is one thing that I did when I was in a class like this, was I overthought, how can this be possible? I'm trying to define the structure, and then within the definition of this structure, I use a pointer to point to the very same structure that I'm trying to define. It's actually not a problem.
As long as you don't like make the cookie right.
Exactly. You're just trying to say, oh, by the way, this cookie contains the instruction to find another cookie.
Right.
So you're not having a cookie inside a cookie. You're
Yeah.
just having the instruction to find another piece of cookie from one particular cookie.
It just looks like kind of like a linked list, like how we.
It is a linked list,
Yeah, right.
but I don't want to use the term linked list because I don't want to. I don't want people to think, oh, this is a CISP 430 concept, and yet we are doing this in CISP 310. Now, there's a big difference between what I'm doing in this class and what they are doing in CISP 430, because in CISP 430, you guys are supposed to write the code. I'm providing the code already. I'm just trying to I'm just trying to use this as an example to translate this code into assembly code. So there's a big difference between what is being taught in CISP 430 and what I'm trying to teach in this class. All right, so if this notation is foreign to some of you, okay, which is not surprising because sometimes they run out of time in CISP 360 and they do not really do much about structures in terms of accessing it as accessing a member of a structure that is pointed to by a pointer. So instead of looking at it this way, you could look at this as as dereferencing point ptr1 first. And once you dereference ptr1, it is just a struct x. Then you can just use the dot notation to refer to its member. So these two lines, line 11 and line 12, are exactly the same thing. It's just that syntactically they look different. Most C programmers prefer line 11. That's why we have that little pointer thingy operator. But it's not necessary because we can also use line 12 to accomplish exactly the same thing. So conceptually, line 12 explains what we are doing better compared to line 11. But in terms of what people actually do, it's line 11. Do we have any questions about line 11 versus line 12? Okay, all right. So I'm just going to delete line 12, just because, I can comment it out. Okay, so this way you can still reference it if you want to. All right, so here's main. Okay, int main. And inside main, I'm going to have struct x AB. Okay, so we have two actual pieces of cookie being defined in main. And let me do some initialization in main. A dot v, well, we'll put 23 into it. A dot b dot v, we'll put 17 into it. And then we'll also put an end to b. So b dot p next is a null. Null is just a fancy name of 0. Okay, so every time you use uppercase null, N-U-L-L, it really is just 0. Okay, so it's perfectly okay to state it like this without referring to null, the compiler won't complain. There's no warning whatsoever because 0 is one of those things that has a magnitude of implicit types. It can be matched. It can match any type that you can throw at it. Or I shouldn't say any, but most all of the scalar type can take a 0 as a value. All right, so now we're going to call the subroutine. So we're going to say link. We'll pass the address of A, pass the address of B, and then return 0. And that's the end of the C code. Any questions about the C code, about what is happening with link? So after link, A is going to have its P next member to point to B, and that's it. But this is enough code that I can illustrate the techniques of how to define the structure, how do we get to members of a structure that is pointed to by a pointer, and also how to get to members of a structure that itself is a local variable. So I can illustrate all of those concepts using this particular program. Are we good so far? Yes? Okay, all right. All right, so that means now we can start with the assembly code. I always start with a no-op because I intend to use reverse spider. And then JMPI to main. You can also initialize the stack pointer here. This would be not a bad place to initialize the stack pointer. JMPI to main. And then we have the subroutine link. Okay. And I'm just going to do the return code as usual. That's just how I write my code. Like so. And now we have main. Main does not return, instead it halts because it is not actually called from anywhere else. Okay, so the biggest question now is what about struct X? How do we define struct X in this case? So as it turns out, struct X is just a template. Okay, that's all it is. So the question is,
You and me both.
I'm going to have to turn off my Bluetooth. Here we go. Because this thing connects by USB and Bluetooth at the same time, so it's actually doing the recording for the PC. But at the same time, the Bluetooth connection is also there, so it's actually listening to. So my phone has been listening to the conversation as well. All right, cool. Um, Right. So the structure itself, okay. So if I were to use an object, okay, in the C code, okay. So in the C code here, if you are comparing b.v and b.p next, those two members, they should be right next to each other, right? Because the entire structure B is one chunk of memory. Within that chunk of memory, we have one little part of it allocated to member V, and then the other part would be allocated to P next as a member. Is that making any sense? So one way to look at that is to look at it as in a picture. So we can kind of use a picture to represent this whole thing, okay, using comments. So when you look at a struct X, okay, I should probably put it over here because I can look at a specific struct X. Let's say we are looking at B, okay? So we are looking at B, and B is going to be, it's going to take up 2 bytes. So the higher byte of B is going to be corresponding to P next as a member, and then lower byte of B is going to be corresponding to V as a member. So B, okay, if I just want to make this look nicer, okay. There we go. So there's a picture. So B as a structure consists of 2 bytes. V is the first member. So typically, we just go by the order of the members. So the first member has the lowest address, and then the last member has the highest address. It doesn't have to be like that. It's not a part of the language specification, that the ordering of the member has to be respected. So the compiler can choose and completely randomize, where each member is within that chunk of memory. But one thing that the compiler cannot do is not to put all the members into one contiguous chunk of memory. They have to be together. Is that okay? So that means, so if I have a pointer to point to the beginning of B, then I can use the offset to each member to get to each member. Does that make sense? So I can now say B is at a displacement of 0. If I have a pointer pointing to B, then B would be right at where that pointer is pointing to. And then P next is going to be 1 byte past where the pointer is pointing to. Does that make sense?
So 1 plus wherever B
Whatever the pointer is. Yep. So that means, in order to define the structure, I can now use labels. So the label, okay, I just hit my key a little bit too hard, and my HDMI cable is being sensitive, so I just lost it for a while. Okay, and okay, so now we're back here. All right, so the way I define this is I use the x as a prefix, and then I specify v is at offset 0 from the beginning of the structure. Okay, so this is offset 0 from the beginning of a struct x, and then x underscore p next is going to be x underscore v 1 plus. So I like to express things in a relative way. So this way, if I need to insert something, it would be fairly easy for me to add additional members into this structure. I also need one more definition, which is the size. So the size of x, or I can just say x underscore size, is the offset to the last member, and then plus the size of the last member. So this way, your x size ends up being 2, which is not really surprising. I mean, I could have just defined p next as 1 and then p x size as 2. But this way, I make it easier for me to extend the structure later on to add additional members and to switch order of the members and whatnot. So it just gives me more flexibility later on. Do we have any questions about how these three labels on from line 5 to line 7 is defining the structure in the C code, which is from line 3 to line 7? So the concept is captured even though the programming language itself does not have structures. Are we good so far? All right. All right, so I'm going to start with main because otherwise there's nothing I can test. Okay, so we'll start with main. Main this time has two local variables, so I need to allocate for the two local variables. So what are we expecting to be on the stack from the perspective of main? Well, the ordering between A and B is kind of not important, but in the previous module, we're going to allocate for A first, and then we allocate for B. So that's going to be what it looks like. Except this time, A is not a single byte thing, and neither is B. So when we allocate for A actually takes up 2 bytes. B also takes up 2 bytes. Is that okay? So when we define the labels corresponding to A and B in main, I'm going to have to define it like this. Main underscore B is at the offset of 0 from where the stack pointer is pointing to. So you have to kind of remember, there are two types of offsets in this particular program. Offset from the beginning of a structure, that's how we define the structure, and offset from where the stack point is pointing to, which is what we have talked about for the past week and a half or so. So in this case, this is the offset from where the stack point is pointing to. And when we need to define main A, it's main B, but it's not 1 plus anymore. It is 2 plus, but I'm not going to use 2 because this is why we have the label called x size. So this way, if I do change the structure and it takes up more bytes or fewer bytes, I don't need to change the rest of the code because I'm referring to a label that refers to that self-calculates the size of a struct x. All right. So next we have the size of all the local variables, okay, LVS. So that's going to be main A, which is the offset to local variable A, um, plus the size of A. So that's going to be the number of bytes that we need on the stack for the local variables. And we don't have a return address, and we do not have any parameters. So these are all the labels that I need. But the labels do not do the actual allocation on the stack. In other words, the stack pointer will still be pointing at location 0 if I don't do anything about it. So I need to adjust the stack pointer using instructions. So this is where we have the LDIB main underscore LBS. We subtract to allocate, and then we add to deallocate. So to copy over here, change that to add. So you can now see the structure of the code is, well, I mean, kind of the same across all of the programs. We allocate for the local variables, and then we deallocate for the local variables. And you can also see the way I code this is by structure. I don't just start from line 1 and move all the way down, because I find that if I write code this way, I won't forget about closing something later on because I close right away, and I just go back and backfill what is supposed to be between the opening and the closing. All right, so the first line to implement is line 18. So we want to find out what we can do with line 18. So I would do the kind of the longer way to do this first, and then we'll talk about how to make it more efficient. Okay, so the longer way to do this is I want to change member V of A to 23. The 23 is easy, okay, so I'm not too concerned about it. So this is one of those fewer cases where I'm going to put more effort into calculating the left-hand side first instead of the right-hand side. So I'm going to make a comment here and say the left-hand side is going to be the following code. Okay, so I need to get to um, A as a local variable first. So that's not too hard. I mean, you guys have seen all this code already. So now A has the register A has the address of A as a local variable, right? So from this, what do we do to get to member V in this case? We need to add the displacement to member V to the address of A. So the way to do this is to use, I can use register B, and that's going to be X underscore V, and also add that to register A. So in this case, it is really kind of important after class at some point to comment each line of code, specifically what line 32 and what line 30 are doing, because they seem to be doing about the same thing. They're adding something to register A, but what they're adding is different, and why they're adding is also very different. One is adding the stack pointer to get to the address of something that is either a local variable or a parameter. The other one is saying, okay, A already has the address of a structure. I need to get to one of the members of this structure, and it's adding the offset to the specific member that we want to get to. So commenting these 4 lines of code is going to be very important after the class is over. All right, so now that I have the address of member V of the structure A, I can now change that to 23. So we'll go ahead and use register B for the value 23, and then STB, oh, STAB, there we go, because register A has the address of member V of the structure A, which is a local variable. All right, well, I just made a lot of claims, right? And we don't know whether this is the way it's supposed, whether the program works or not. So we can actually test run this program. This is why getting River Spider up and running is useful, because you can basically just go write a few lines of code, run it, observe whether it is doing what you think it should be doing, and once you get a confirmation, then you know, okay, this is good so far, and then move on and continue the coding of your program. Because it doesn't make sense for me to write any additional code unless I know this part is working. Is that making any sense? All right. So let's go ahead and do this. Okay, let's run this first. But before we run it, we also have to understand what are we supposed to see when we run this code? That's the question. Okay. So what would be the side effect that we should be able to observe in the analysis tab of the assembler?
We should see we should see that register A has 23, right? And then the
No, I mean it's register B that has 23.
so register B has 23 and register A has the value of B. So B dot B.
No, register A has the address of member V of A as a local variable. So we want to be able to see that, right? We want to be able to observe. So okay, so this is important. This is like super duper important. Is can you visualize what is supposed to be on the stack at this point? That's really important. So let me go ahead and just use a table, which is a spreadsheet, to illustrate what is supposed to be on the stack. All right. Okay. All right. So we start with location 255, 254, 253, 252, 251, 250. And I think this program only needs 6 bytes. Nope, it's going to need a few more, but we'll not right away. Okay. All right. So the first question is, where do you think we will find local variable A and B of main? Let me show the code on the side, so this way you can actually see the assembly. Okay. So this way you can actually see the assembly code and also the spreadsheet at the same time. I'm going to change the way I change focus. So this way I can actually type in the spreadsheet without um, getting rid of the program. So you guys can focus on this first to try to figure out which location has A, or which locations your plural has A and which locations have B, and where the members are within each structure. So I'll let you guys do that first while I'll be tweaking some of the settings to make it easier to switch with between the two screens. Okay, focus. Do not raise window. Okay, all done. All right. So where am I supposed to find local variable A and local variable B? So variable A is allocated first, so it will have the highest locations of the stack. So the stack is currently empty before the allocation. So that means register A is, I mean, not register, but local variable A is going to take up locations 255 and 254. That is correct. So I go to the spreadsheet and then we just, kind of add our annotation here and say this is going to be, both of these locations are for local variable A. Which one is corresponding to member V and which one is corresponding to member P next?
Isn't that arbitrary?
It is not arbitrary the way we have already defined X
Oh,
as a structure.
P dot next. P next is going to be first, and V is going to be second.
Why is okay? Tell me which location. Location 255 is which member? It has a higher address, so it has to be, and we are allocating for the members in the order of the members being listed in the structure. So what is location 255? Which member of A is corresponding to location 255? It will be P next, because P next is the second member, so it has a higher address. So location 255 is corresponding to A dot P next. This is corresponding to A dot V. Is that making any sense? Because within a structure, we allocate memory according to the order of the members as listed in the structure definition. And in the structure definition, in the C code, we had V first and then P next. So that's why your V is the first item within a structure, within the struct X, and then P next is the second item within the P next. Is that okay? I'm not hearing any questions, but I think there might be questions among this class. So unless you ask the question, I don't know what the question is. I just know the existence of a question. Yep.
Where would the variables go? Since, I'm sorry,
Say it one more time.
the local variables.
The local variables. Oh, these are all local variables.
Yeah, but I guess with main A x size plus.
X size is 2, right? So that means we are allocating 4 bytes altogether for my local variables. This is just one of them. A is one of them, B is the other one. So if I were to complete the picture, then we would have B dot P next here, and then B dot V over here.
Oh, so it's just the size of.
And that, yeah, so all 4 locations here are local variables for main. Okay, question? Okay, so I'm not sure whether there are still questions or not. All right, well, I'm going to assume that there are no questions because I cannot read minds as much as I want to.
So I do have a question.
Yes, go ahead.
When you said left-hand side, are you talking about the stuff that's in white versus stuff that's in blue on the C side? Like, what is left-hand side referring to? Left-hand side of what?
Left-hand side of line 18 as an assignment statement.
Okay.
So far, okay. So in the assembly code, line 29 all the way to line 32 corresponds to the address of line 18 in the C code. So it corresponds to the left-hand side of line 18, which is an assignment statement in the C code. That's how we compute the address of where we can find A dot V. Okay, I can sort of show you guys how it is all done because the stack pointer is going to be pointing at location 252 at the time when we get to line 29. So the first thing we do is we have to find A first. So we load main A into register A, which is just 2. Since the stack pointer is pointing to location 252, so register A is 2. So when we add the stack pointer to register A, it would point to location 254. So that's how we end up with the address of the entire structure. But of the entire structure, it has multiple members, and we want to access a particular member, which is member V. So we have to load the offset to member V into register B on line 31 of the assembly code, and then add that offset to the address of the structure itself. So in this case, it looks like it is not useful because the offset to member V is just 0. But having the code looking like this means later on I can insert an additional member before member V, and it would not disturb the code. The code would still work. So that's why I always want to refer to the label name and not to make the assumption of that's just 0. We don't have to add because if I did those optimization, then the code is not going to be flexible. And the moment I change the ordering of the members, that this program is going to break. All right. So are we good to move forward? More or less, okay? Now, this is also why looking at the trace can also be helpful. So I'm suspecting this program is going to get the job done. In other words, I'm expecting a.v to be changed to 23. Okay, if I just move this a little bit here, this is what I'm expecting as the outcome of this program. Is that okay? So the trace can tell me whether it is getting the job done or not. And that's why it is important to run the trace, but only after you understand what the program is supposed to do. All right, so we'll go ahead and run the river spider. And let's see where. Oh, we can get out of this one. There's no need to keep here. So we go to Documents, CISP310, river spider, and then submit struct.ttp. Oh, I did forget to save it, didn't I? struct.ttp-asm. All right, so the code is already done, and it is on this side. All right, so what we're looking for is, okay, let me double check, right? Go to my own local spreadsheet. We're expecting, this is FF, this is FE, this is FD. We're expecting location FE to change to the hexadecimal representation of 23, and that's 17 because it is 16 plus 7. So let's double check, okay? So we're looking at RAM writes, okay? There's only one single RAM write here, and it did change location FE to 17 in hexadecimal. So the program did what it is supposed to do. Is that okay? All right. So if you want to take a snapshot of this assembler at this point, go ahead and take a snapshot, because once you take a snapshot, you can now start to use your own comment, using column H and all the other columns to basically add your own explanation of what each line is doing. The analysis tab is different compared to the source tab in a major way, because if you look at the source tab, it is simply describing what instructions are supposed to execute and so on and so forth in which order. But when you look at the analysis tab, not only does it show you what instructions execute, but it also shows you the outcome, the result of executing the instructions. So this makes it more it makes it easier for you to look at this as a concrete case of, oh, I see register A is now blah blah, okay, and that is the beginning of the entire structure. And now, register A has the address of a particular member of the structure. So it makes it easier for you to actually, it makes it more concrete, and hopefully makes it easier to understand. Are we okay so far? All right. All right, so getting back to the code, okay, and we want to be able to finish this entire program. So the next thing we need to do is kind of the same thing, except this time we are trying to put 17 into B. So it would be the same kind of structure, 1, 2, 3, 4, 5, 6 lines of code. So I just copy and paste it, and this time it is it's local variable B, and the constant that we want to store is 17 in this case. So I'm not going to test run this code because it's kind of, well, might as well, right? Okay, so in this case, it's going to change which location to what. So let's go back to the memory map here. So this time it's going to change this location, which is member V of B, to 17, which is 1, 1 in hexadecimal. So we are now expecting location FC to change to 1, 1 in hexadecimal. Okay. Now, this is also why setting up River Spider is useful, because you can literally just write a few lines of code, run the whole thing again, and get a confirmation whether that is doing what you expect it to do or not. All right, so it's all done. Go back to the analysis tab, and we can see right here, location FC is changed to 11 in hexadecimal. So now I get confirmation that the structures are in fact initialized correctly. All right, so getting back to the code, now we tackle the third line here, which is changing p next of b to null, which is 0. Yeah, it's about the same thing. So I'm just going to copy these 6 lines of code. Okay, maybe here. There we go. And this time I just need to change the member from v to p next. And the value that we assign to that location is going to be 0. Okay, there we go. And that should change if I go back to the memory map. So this time, P next as a member of B as a structure should now be changed to a 0. It would not be observable if you just look at the RAM content, because all the locations of RAM are initialized to 0 to begin with, but the trace will still show you that that location is a 0. So you can still actually see it in the trace. Are we doing okay so far with this code? Okay. I just forgot to do one thing because I said earlier that these can all be optimized. Now, why can they all be optimized? Because if you look at what we are adding to register B, we're adding x underscore v to register B. I take it back. So if you look at what we're adding to register A, we're doing 3 things to register A. The first one is I initialize register A with the offset to find local variable A. That's the first thing we did. The second thing is I added register D to register A, and then I added basically x underscore v, which is the offset to find member V, also to register A. So we can actually combine those additions, or at least 2 of those can be combined. So I'm just going to use this one as an example of what we can do to combine. So instead of doing this, I can now say, might as well just put this also here. Then we don't need this. Because adding constants twice to the same register means we can combine those 2 constants into one single constant, so we can save a few instructions this way. Is that okay? I could do the same optimization with the other 2 instances. Yep, go ahead.
Oh, sorry. It's just a little tricky to read, but I see what's going on. It's essentially a constant that you're loading, and you're adding the 2 constants. So it's essentially one thing, one value loading into it.
Yeah, register A ended up with being the sum of 3 items, right? So by the time we get to line 39, register A becomes the sum of 3 things, which is main underscore B, that's a constant, register D, which is not a constant, and then x underscore V, which is also a constant. So of the 3 things, 2 are constants, 1 is not. So we can fold all the constants into one single thing by adding those 2. Then we can save the code to load the constant into register B and then add register B to register A, because that's not needed. I mean, is it wrong? No, it is not wrong. I mean, if you compare the code from line 36 to line 41 versus the code from line 43 to line 46, they're both correct. It's just that one has 2 redundant instructions, so I'm burning execution time for something that I really don't need to burn execution time on. All right, so I can now do the same optimization over here and just say this is x underscore v plus, and then we can get rid of these 2 lines, and the same thing over here. And get rid of these 2 lines. Now, I just made a bunch of changes and claim that, yeah, the program should still work. Do I want to count on my instinct and gut feeling that the program is probably going to work just like before? Or do I want to test it? What do you think?
Test it.
Exactly. You have no confidence in me. That's good. That's actually a good thing. So it's almost done. Let's switch back to the trace and find out whether the program is still doing what it's supposed to. Yep. Okay. So it still got all the bytes initialized the way that they are supposed to be initialized. Okay. Very good. So now we move on to the actual meat of today's class, which is line 21 of the C code. Well, okay, that and also inside the subroutine itself. But the first thing we need to do is to push the address of B and then the address of A on the stack, and then we push the return address, and then we jump to link. Okay, so let's see how we can do that. Okay, so LDIA with main underscore A, that's the offset. Add AD, that's the address. Woohoo! That's all I need. Okay, that's actually not right because we need to push B first. Okay, the address of B. Now we do have the address of B in register A, so we just have to push it. That's how we push the address of B on the stack. And then we can do pretty much the same thing with A as a local variable on the stack, except this is going to be a little bit problematic. Okay, I'll explain why it is a little bit problematic and then also to explain how to fix the problem. I believe this is something that I have mentioned already, because right now, after this decrement D on line 46, the stack pointer is no longer pointing to the, the lowest local variable byte anymore, which was the assumption when I defined the labels.
Is it because it's a structure, so there's two things there now?
No, it has to do with decrement D. It has to do with on line 46. We were pushing the second argument on the stack, so that forced the stack pointer to be pointing to one byte lower compared to the assumed location when we created those labels. In other words, in the memory map over here, when we push the address of B on the stack, and that turns out to be 252. The stack pointer, the stack pointer is now pointing here instead of here. So when we created the labels, we were using the assumption that the stack pointer would be here. But the stack pointer is actually pointing here at this point because we just pushed the return, we just pushed the address of B on the stack. So all the offsets are off by 1 at this point. So in the code, to compensate for that, I have to say, well, guess what? The stack pointer is now 1 byte lower than where it is supposed to be, so we have to compensate for that 1 extra byte on the stack. That 1 extra byte is corresponding to the second argument of calling link. We do okay so far? When you run the code and look at the trace, it will be clear. Okay, so we'll put the address of A over here, which is 254, and then now we have to push the return address. So LDI A dot 5 plus. Oh, we need a decrement D first. And then we have a SDDA. That's the return address. And then we can now jump to what is the link. And when we get back, we have to increment D twice because we have 2 arguments still sitting on the stack. And increment is going to be fine because I have the addresses of the structures. I actually do not have the entire structure on the stack as my arguments. It's just the pointers or the addresses. Are we still doing okay at this point? Or do we have any questions? So all this code here is really just setting up the call to link. I need to push the address of B. I need to push the address of A. Then I will get it up to link to do whatever it needs to do. Is that okay? Maybe. So once again, I'm not a mind reader. I can sort of feel that some people may have some questions, but I cannot know exactly what the question is. I'm being as useless as Counselor Troy of Star Trek The Next Generation.
We're sensing uneasiness, but
I mean, Deanna Troy would basically watch the Klingons having a fist fight on the screen, and then she would say, "I sense anger." It's like, yeah, I think I can see that too. So, do we have any questions other than what are Klingons and so on?
Because
Yeah.
it wasn't clear when that was talking. What is the 0.5 plus 4?
Huh?
The 0.5 plus 4.
The 0.5 plus.
What's adding 5.5?
Looks like line 55.
Okay, so can someone in the class answer the question? What is the 0.5 plus?
it's an offset, right?
Go ahead.
So it jumps 5 lines ahead when you return back to me.
5 bytes ahead. 5 bytes ahead. It jumps 5 bytes ahead because the dot refers to the address of the LDI. LDI itself has 2 bytes. So we have byte 0, byte 1. This is byte 2. This is byte 3 and 4. So this is byte 5. So this is how I can specify the return address without using a label. If I know what the next few instructions are, I can pre-compute how many bytes I can adjust for that. Mm-hmm. All right. Any other questions? So watching some of the previous lectures can be helpful, especially if you miss one. Make sure that you watch that video. All right. No questions? Well, I'm going to run the code, and someone is going to say, "But Tech, you didn't do anything with link." That is correct, but it will still return, right? Yeah, and that's all I need link to do right now is just to return, because I want to make sure the stack is balanced and the right kind of stuff is on the stack and stuff like that. So I'm expecting the stack to look like this, and this one is going to be the return address. I really have no idea where that is until I run the assembler. I won't be able to tell. But I know that I'm going to use locations from 255 all the way down to 249 when I do run this code at this point. Okay, so we'll give it a try. This is basically why I set this up why I set up this tool is just so that it's easier for me to test run the code a lot quicker. All right, so let's check out what is happening. This is the null character, okay, from before. And okay, I know what happened. My favorite stupid mistake, not saving the file first. So yes, having an IDE can be helpful. Maybe I should make running River Spider a command in Vim, so it will automatically save the file and then run run River Spider. Maybe one of these days. All right. What is this FC here? This FC is okay. So this is at location FB. I'm changing location FB to FC. Let me see. Is that correct? Yep. Okay. So where's FB? Let's go back to the memory map here. Which one of these is FB? This is FF, E, D, C, B. And it is supposed to be the address of B, which is at location 252, which is FC. So the question is, did I put FC into location FB?
Yeah.
I cannot remember. I really cannot. Yes, so I did. So the next question is, did I put the address of A into the next byte from the stack? And I did. FE is indeed the starting point of local variable A. So this is why you can see how this 1 plus here is important, because without this 1 plus, I would have pushed the wrong address on the stack. All right? Okay. But more importantly, did I go call the subroutine and return from the subroutine correctly? This is the return address. And then I get into the subroutine returns to location 2D, and I deallocate the 2 arguments on the stack, and then we deallocate the 4 bytes of local variables from the stack goes back to location 0, 0. We're all good here, okay? So now it is finally time to actually implement the one statement in link as a subroutine. So there we go. Let's switch back to this tab here. So now we are finally ready to implement line 11 in link as a subroutine, which really is the highlight of today's lecture. Really, seriously. So now we want to look at the map again. We have PTR2, we got PTR1, we got the return address. There are no local variables in this case. Well, guess what? I can still say link LVS is 0. There's no harm done here, okay? I'm just using up one label, but it does give me the provision of easier to deal with the program. If later on I need local variables, I have the structure for that already. All right, so we need to find PTR1. Okay, PTR1 is link LVS1 plus, and then link PTR2 is link PTR1 1 plus. So I got all the labels done. And even though we have no local variables whatsoever this time, it doesn't hurt to allocate, okay? Because I can still say, let's go ahead and allocate LV as this many bytes on the stack. You guys are going to go like, but that's useless. You just spend some time to optimize some instructions. Why are you wasting cycles in this case? Well, I'm wasting cycles in this case because this way, if I do need local variables later on, I don't have to remember to insert the code to allocate and deallocate the local variables. Okay? So yes, it does burn up a little bit more processing time, but it does give me the flexibility of doing something later on. So personally, I would say this is not a bad trade. All right, so we need to get to PTR2. So the code to do that is link PTR2, add AD. That's the address of PTR2, and we need to do an LDAA to actually get to the value of PTR2. This is the right-hand side. The left-hand side is, the last 5 minutes of this class is the super highlight of this class, is how do we get the address of a member of a structure that is pointed to by a pointer that is a parameter, which is also living on the stack. So this is the super highlight of this entire class. If you get this part and go like, yep, I know exactly what is going on with every single instruction, you're doing fine in this class. Now, if you need some time to review the material after class and go like, okay, I need some time to work this out, that's fine too. Not a problem, okay? But the important part is, I hope by next week, by the time we have the final exam, which is the week after that, we all feel comfortable with these few lines of code. All right, so to get to this one, the first thing we need to do is to get to PTR1. Okay, I don't think anyone is going to argue that we have to get to PTR1. So we do LDI. I cannot use register A because that's the right-hand side. I'm going to use register B, link PTR1. That gives me the offset to get to PTR1 as a parameter. But since that offset is relative to where the stack pointer is pointing to, I need to add the stack pointer to the offset to get to the address of PTR1. Okay, cool. I get to the address of PTR1, but I need PTR1, which itself is the address of the structure that I need to access. So I need LDAA. Oops, wrong registers. Okay, there we go. So I need LDBB to get to the value of PTR1. The value of PTR1 itself is a pointer pointing to the structure of which a particular member I need to access. So right now, register B is the address of a structure. but I need to access a particular member of the structure. So that means I need to add the offset to it. So the offset in this case is x underscore p next. I put it into register C first, and then I add register C to register B. So now register B, it used to point to the beginning of a structure. Now it points to the member P next of the same structure. Is that okay? All right, well, that's all I need. I just need the address of member P next of the structure that is pointed to by PTR1, which itself is a parameter living on the stack at a certain displacement or offset from where the stack pointer is pointing to. So once I got everything in place, that's all I need. All right, so I claim that this program is done, okay? So we're going to test run it. Remember to save the file first, because I typically forget to do that. And then we can go ahead and run it one more time. But we also need to know what happens when we run this one more time. So we're looking at the memory map here, and we're asking, well, when this is all done, what are we supposed to see? Well, P next of A is supposed to change to point to the beginning of P of B. So that means location 255 would contain the address of B. The address of B is 252. So we're expecting this location, FF, to be updated to FC. So the value of location FF should update to FC. Okay, that's what I think it should do, right? So now we go back to the trace here, and then we keep going because this time I actually have the code, and that's it. Is that okay? But I also want to make sure that in this process, I did not mess up anything. So I really kind of need to make sure that when I do go back to main, which is here, this is where it returns to main. I increment the stack pointer twice to get rid of the arguments. And then we add 4 to the stack pointer to deallocate the 2 local variables. And then the stack pointer is going back to location 0, 0. The whole thing is done. All right, so do we have any questions about this program? I know we're running out of time, but as I said, the last part of this lecture is really the essence. I mean, if you feel comfortable, I know exactly what each instruction is doing, then I think you have a pretty good understanding of the material, but still, I think it is important to document and comment the program and explain what each instruction is doing in your own words, relating the instruction itself to the C code, what is happening on the stack. And one thing that might be helpful to you is to draw a picture. So I use a spreadsheet for this purpose, but the spreadsheet doesn't let me draw arrows, okay? Because if I were to draw arrows, I would have drawn an arrow going from here to here. So this will be an arrow because it's a pointer. That really is a pointer. I would also draw an arrow from here to here, another arrow from here to here, because those are pointers also. But I don't have the capability to do that in a spreadsheet, not easily. So I will leave that up to you, because that would give you the idea of what is a pointer, where does it point to, okay? And I would also kind of group these things so that you can understand that both of these bytes are a part of variable A of main. Both of these bytes are part of variable B of main. And this is parameter PTR2. This is parameter PTR1. This is the return address. This byte is not used. So the lowest we got is location 249 in this particular program. So are we good so far? We just used 80 minutes to talk about a lot of the concepts. So I hope you guys know what to spend your 160 minutes of outside of the lecture time, for this class. I'm only half kidding when I said the 160 minutes of outside of class time because I know some of you do not. And but that's the assumption. When you take a class, you're assumed to spend 2 hours per every hour in lecture to study, to kind of go through the material, to review and stuff like that. So having enough time budgeted for a class is super important. Are we okay so far? Now, I also want to emphasize that I have office hours as well. So if anyone is feeling that, okay, I need a few sessions to kind of clarify some of the concepts or I have some questions, do not hesitate to use my office hour. It's 1 hour before this class. My office hour starts 1 hour before the lecture. So I just hope that that is convenient enough for most of you to utilize that time. All right, so if there are no questions, I will release the lab of today. So the lab for today, I'm kind of skipping the recursive call homework assignment. So we are jumping a little bit ahead to structures and pointers, which is, guess what we did today. So this is our assignment. And there, it's kind of like the swap subroutine. A part of this is due today, and then one part is due sometime next week. So let me set this up, and it will be this part is going to be due at 1:30 p.m., which is the usual time. And let's see, does it have a passcode? Nope, doesn't have a passcode this time. Save and publish. So this is the first part, which is due today at 1:30. It's not going to take you a whole lot of time for this part. The part that will take you quite a bit of time is going to be the actual coding part. All right, so let me get back to this part here. This is the actual coding, not the recursive one. Structure and pointers code submission. So this one I will give you guys until next Wednesday is going to be too close to the end of the semester. So I'm going to give you guys till next Monday. All right, so next Monday is the 5th. Okay, so December 5th, right before class. So that would be 10:30 a.m. There we go. Save and publish. So there you have it. Okay, you have the programs. And I'm going to upload today's sample program as well because I think it is going to be useful. So let me upload that first. And that means I have to save the programs and then zip it up. All right, so the sample code is uploaded. You guys can unzip it. But if you have access to the computer right now, I would also just take a snapshot of the assembler for today. So this way you have everything already in place if you want to study the sample program that I did today. Alrighty, I'm gonna stop the recorder and upload today's lecture.